we'll read this problem out, and then we'll try to see if we can deduce it. I'll tell you, a lot of times with trig, really helps if we can get pictures along the line. So I'll give it a read. A 3-meter ladder can safely be used at an angle of 75 degrees with the horizontal. How high to the nearest meter can the ladder reach? Okay, so drawing is not what I'm best at, but I love to draw. So here's a ladder that might have some things that are not so straight. Yeah, watch out for that step when you're on it. Okay, so we have a ladder, and we know it's 3 meters tall. Okay, but we can't just hang ladders in the middle of the air. They don't work so well. You got to be really balanced to use it that way. We usually lean them against some wall, right? So let's say this is our wall here. Here is said wall. And walls usually touch ground. So we'll put a ground also. The reason I'm doing that is because there's a very important word they mentioned here. They said with the horizontal. Do you know which of these two lines is horizontal? Would it be the one up here? The bottom one, yeah. So we'll call this the horizontal, and this is the vertical. Okay, so the wall is vertical here. We make an assumption that the wall makes a 90-degree angle with the horizontal. It's possible the wall is not even straight, but we're going to make this assumption, okay, just to make the question a little simpler for us. And then I'm going to lean the ladder up against the wall. I should do it in black since that's what we originally had the ladder in. Okay, so we have some ladder. Make it look more like it's 3-dimensional. Oh, yeah. Soon I should be doing art. Okay, we got our ladder against the wall. It makes an angle with the horizontal. So that's what's really important, because technically there's two angles, right? There's an angle it makes here and an angle it makes here. But when they say with the horizontal, we know it's referring to this line here. It makes one of 75 degrees. They could have said with the vertical, and then they're referring to this angle. As a side note, do we know what the angle is with the verticals, with the two pieces of information we have at the moment?
Yeah, the bottom one's 75. I don't think we know the other one.
Is there a way to know?
Well, yeah, you can like add, like all of them make 180.
Perfect, yeah. So I can say the angles of a triangle, so I can call even, angle 1 plus angle 2 plus angle 3 are always 180 of a triangle. I know angle 1 we'll say was 90 plus 75 plus, I don't know what angle 3 is at the moment, but I can do some quick algebra. And I know that 180 minus 90 minus 75 will be what that angle is. And angle 3 in this case will actually be equal to 15. Okay, degrees. Everything was in degrees. So this one is 15 degrees. We'll just put it up there as a helpful piece of information. How high can the ladder reach? So that's what they're getting at here. How high can this ladder reach? Well, we'll say that this is... Oh, red's not the color I want. Let's go blue. We're looking for that distance right there. So we need to solve this. We will call this, like we so often call something we don't know in math, we'll call this x. We don't know what it is. Okay? But in triangles, I want you to make a point that there's actually 6 pieces of information that are usually pretty essential for triangles. And those are the 3 angles. Okay, 1, 2, 3 angles. Have you seen this? It's called theta. Have you seen that symbol yet? A little bit.
Does it just mean angle?
Yeah, it's really just a variable. I could use x, y, and z. I'm going to use theta. We'll maybe call it theta 1, theta 2, and theta 3, okay? Theta is commonly used in mathematics to represent an angle. It's a Greek letter that we usually use in that sense, okay? But we also want to know the side lengths, which, I mean, you can call them A, B, and C. I'm actually going to call the other one C, just because it makes a little more sense with Pythagorean's theorem. But you can technically name things anything you want. So keep that in mind with triangles. That's 6 pieces of information. In the current triangle we're looking at, okay, we actually have 1, 2, 3. We have the 3 angles, so I'm going to give them checks. Angle, angle, angle. Do I have any of the sides? I don't have side B here. We called it X, right?
Yeah.
Do I have this part at the bottom?
No.
No, I don't have that. Do I have this part here, the ladder?
Yeah, 3 meters.
Yeah, that's 3 meters. Very good. So we do have that. There we go. So we got another piece of information. This is good. Now the question is, how do I use the pieces of information we have to solve what we're looking for? Remember, you have a couple options. You have something called sine law, cosine law, and then I'm just going to write it as Sohcahtoa, but these are 3 formulas that represent trig ratios. Here's my question. What can you use? Because this is actually the harder thing to figure out. Which tool do we use? Maybe you can use more than one tool.
I think one of them, well, are the sine law and cosine law for non-right angles.
Ah, okay. So, first of all, I spelled law wrong. Did you notice that? I just noticed that. I called it last there. You can actually use these. These are far more powerful. These can be used for all triangles.
Really?
Yes.
Why
These
did
ones are actually super specific. There's a specific type of triangle that they can only be used on.
Is that just a right triangle?
Yeah. They can only be used on triangles. Right? I almost spelled that wrong. Right triangles. So keep that in mind. Technically, sine law and cosine law are more powerful, and these are just little shortcuts when you have right angle triangles. You can use sine law and cosine law. The reason we don't is it just takes longer to use those laws. They're a little less efficient. We've come up with simpler tricks to get through it. It's a faster tool. Think of it like a power tool instead of doing it manually. It's not wrong though. So if you ever don't know which of can I use Sohcahtoa? Just revert back to using sine or cosine law. You can always use those, okay? They're just a little more complex, that's all. So we're at a point here. Can we make a decision on which tools to use? What type of triangle do I have?
A right angle?
Yeah, so I can technically use any of these tools. Which ones do you want to use?
We'll do the last one.
Sure.
Because I know that the least, I think.
These 3? Sohcahtoa?
Yeah.
Okay. So let's work with Sohcahtoa. I'm going to actually write them out. So is just a acronym that means the sine ratio of sum theta is equal to the opposite side of the triangle divided by the hypotenuse. Okay? In other words, they'll draw it like this. Sine theta is equal to O over H. That's why they call it SOH. That's your SO.
Oh.
Ka is just cosine. C stands for cos. Theta is equal to the adjacent. Okay? And we'll talk about what opposite and adjacent are of the hypotenuse. And in other words, they'll write it like this. Cos theta is equal to A over H. A just means adjacent. H means hypotenuse. And toa is tangent theta is equal to the opposite side over the adjacent side. Okay? In other words, tan theta equals O over A. So that's why they've written it that way. It's kind of a way of writing an acronym to remember this. These are actually ratios. This is some ratio, another ratio, and another ratio, okay? When we look back at it, we can try to start filling information in, okay? Now, we solved for 15 really early on in the question. We didn't have to. We could have just worked with 75. The angle you're working with is actually really, really important. So we have to make a choice. It doesn't matter. As long as we have that angle, it can be really helpful. What angle are we working with? We're going to say we're working with this one here. So if I have that angle, I need to establish what the adjacent, opposite, and hypotenuse sides are in reference to this angle. Okay? So I have 75. What would be the adjacent side? I'm also going to call this side y, okay? What would be the adjacent side?
I think y.
Yeah, it's the one touching that, okay?
Yeah.
What would be the opposite?
X.
Yeah. And the hypotenuse?
The 3 meters.
3 meters, yeah. So hypotenuse is usually pretty easy to establish. It's opposite of the 90 degree, right? Opposite, the word we're pretty familiar with in our language, so we can apply that. Adjacent is one that's harder to remember. So a lot of times I would just go by deduction. I'd go, well, I knew this was hypotenuse, and I know that's opposite, so this must be the adjacent, okay? Just in case you're not too familiar with that word adjacent. So now that we have that, I'm going to try filling out all three of these, okay? So we have sine theta equals opposite over hypotenuse. Well, theta is actually our angle. So sine 75, I have that info, is equal to the opposite. In our case, the opposite was actually side x, in blue, over the hypotenuse. And the hypotenuse was 3 meters, correct? So we'll say 3. I'll do the same with cos. Cos theta is equal to the adjacent over the hypotenuse. Cos 75. I'm doing a little overkill, okay? And there's a reason I'm doing this. I want you to get the idea. The adjacent side was side y, as you said, and the hypotenuse was 3. And then tangent. Tangent theta is equal to the opposite over the adjacent, which means tan 75 is equal to x over the adjacent was y. Okay. Looking at this, we can establish that there's one of these we can't use. We've kind of hit a sticking point with one of them. Do you know which one it is?
X over y.
Yeah, the tangent one. We can't use it because I have 2 unknowns. I only have 1 of the known. And to use these ratios, I need to know 2 out of the 3 things. So this one we got to stop. Can't go any farther, okay? The next question is, which of these 2 do we use? Because it looks like I have enough information. Which would I use?
I have no idea. Does it matter?
It matters only a little. They'll both give us answers, but the original question read, how high is the ladder? Which of those was representing the height of the ladder?
Oh. The first one.
Yeah, x. So there's nothing wrong with, I'll circle it in blue here. This is the one we're going to keep going with. There's nothing wrong with doing this. It's just not going to get us to our answer, and we'll have to do a couple more steps to get there, okay?
Yeah.
So the more efficient one is sine. So we've set up sine. You can do this every single time. Set up all 3 and just kind of do a little deduction. Eventually you'll get good at recognizing that, I'm just going to use cos. Cos will get me there the fastest, right? But there's nothing wrong with taking roundabout ways. I'll actually do it with cos and show you that it was just a few more steps. Okay, we're here. We have sine 75 is equal to x over 3. How do I isolate for x? What do I do here?
I don't know.
You can, because this is divided by 3, we can multiply by 3 both sides of the equation. The idea of balancing an equation, you have to do whatever you do to one side, you can do to the other. And the reason we do that is because 3 divided by 3 just creates a 1, or they commonly refer to it as canceling out. So you'd end up with 3 times, I'll put it in brackets, sine 75 is equal to x. Okay? Sine 75 is something we'll put into a calculator to find out the exact value. Do you have a calculator handy? I'll see if I do.
Yeah.
Do you want to type that in real quick for us?
Oh wait, how do you... I have to change it to a degree?
Yeah, make sure your calculator's in degrees because that actually makes a difference.
Oh, I think it is. Wait, I haven't used this calculator yet, so I don't know. know if it's working. I just hit the sine button and 75.
Yep. Try typing in 75 and then hitting sine.
Oh, 0.96.
Yeah, that was right. 0.96. I'll tell you one thing, the sine, it's always going to be 0 point something for your sine ratio. Anyways, we have it. And now I just got to multiply 0.96 approximately times 3. So what's that number times 3? It's going to be... Is it 2.88? That makes sense. Yeah, 2.88. So when we go back up, and that makes sense, the actual maximum height you can reach is equal to 2.88 meters. To the nearest meter, that's a silly thing to say. How high to the nearest meter? I mean, the nearest meter would be 3, but we know that can't be the case because it's on an angle. You can never reach 3. You'd have to push it right to the wall. It should have said to the nearest, like, tenth of a meter or something. Let's leave it as our exact answer, 2.88. I want to do one other thing. I want to show you how we could have used cos. Let's say we took the wrong route and then discovered it after. Same idea. Cos 75 is equal to y over 3. We multiply by both sides by 3, where you get kind of a canceling. Y is equal to 3 times cos 75. Now, cos 75 is going to give us a different value. I don't know what it is off the top of my head. Let me see if I can get it here quickly. I haven't memorized that stuff, which I don't think many have. There you go. 0.26 approximately. I'm doing a bit of rounding, which will then mean y is equal to 0.78. Okay? So this distance here, how far from the wall we'll call it, is 0.78. Well, if I figured that out and I went, oh shoot, I gotta figure out this piece, I could just jump back into my ratios, or I could have used Pythagorean's theorem at that point, right? Remember, this is a right angle triangle where we have a squared plus b squared equals c squared. We knew the hypotenuse, which is c, was 3, and a and b doesn't really matter, so I'll just say a squared is equal, plus 0.78 squared, and we could have worked this out. A squared is equal to 3 squared minus 0.78 squared, okay? I'd figure out what those values are, which are like 9 and... what would the other value be? I have the original one, so I'll get a more exact answer. Minus 0.6698-ish, something like that, a squared. Actually, now that I come to look at it, it's definitely not faster, but that's okay. This gives me 8.933 approximately. I would then find the square root of this number. And if I find the square root of this, let's say, change it to that. Square root. Oh, look at this. I got a value of 2.98 meters. So, and I used a little more exact numbers. It's very close, but not the same. I'm actually off by 1/10 of a meter, which is 10 centimeters. I'm off by 10 centimeters. In the real world, not huge, but possibly for answering this, because of my rounding, see how there's a bit of discrepancy here, okay? It's probably somewhere in between the two of them, to be honest. But we've got two answers. If we went the wrong way, there's always another route you could have taken, okay? So just keep that in mind.